Hello everyone, welcome back to this online class. Today we are going to look at finite difference operators. We are given this question. We are asked to discuss the finite difference operators and hence work out the following questions. Number one, we are asked to express each of the following differences in terms of functional values. In part A, we have the forward difference of F3, part B is the backward difference of F6, part C is the shift of F4, and part D is the central difference of F5. Part E is the averaging of F5. Part F is the second shift of Fi. G is the second forward difference of Fi. H is the second backward difference of Fi. I is the second central difference of Fi. And part J is the second averaging of Fi. Part K is the third forward difference of F2. Now, number two, we are asked to verify the following relations. In part A, we have the shift operator is equals to identity operator plus the forward difference operator. Part B, shift operator is equals to identity operator minus the backward difference operator, everything raised to -1. Part C, we have the central difference operator squared is equals to forward difference operator minus backward difference operator. And part D, we have the averaging operator times the central difference operator plus half of the central difference operator squared should give us the forward difference operator. So I want us to discuss the basic concepts involved in finite difference operators. So we are going to start from what we know to be able to build up on these operators. So I want us to take note that suppose we have a table. Suppose that we have a table of x and f of x in the form this one. Let me draw it. We have x values and then we have f of x. So let's say here that the value of x here is a. Here it will be f of a. If I add a constant value so that I have a plus h, here I have f of a plus h. Similarly, a plus 2h, remember the step size is 2h, here it will be f of a plus 2h. Proceed, a plus 3h, here it is f of a plus 3h. And you proceed in the same manner. There are so many other values we have left. So the x values, these are called tabular points. They're called tabular points. And the f of x values, f of x or the y values, remember y is the same as f of x. So the f of x values, we always call this as functional values. Functional values, or they are also called nodes, or you can also call them the base points. So we have three names that we refer to them, or simply tabular values. Let me call it tabular values. Or functional values, or base points, or even base points. So this one has four names. functional values, nodes, base points, tabular values. So usually, when you have a table of this form, we can decide to denote the x values. Like here, we can start and say, let this be x naught, this is x1, this is x2, x3, in that manner, so that here we'll have f naught, f1, f2, f3, in that manner. What we are calling, in general, when we write f of I, it simply means f of xi. So we abbreviate that by fi. So when I write x naught, it's the same as the value of f when x is x naught. So you can just write here e.g., what we are calling f naught is the same as f of x naught. Also, f1 is the same as f of x1, etc. So you can just write here etc. Now, again, this h here is called the step size. It is the step size, or there's a better name that we refer to it. It is called the interval of differencing. Interval of differencing. Or the step size. So these are basic concepts involved in finite differences. So just like as I have explained that fi's, the x values are tabular points and the f of x values are functional values. Now, having explained those concepts, let us now define the finite difference operators. So now the finite difference operators, finite difference operators. Now they will operate on functional values. Let us discuss them. There are about 6 operators. The first one is what we call the identity operator. Number 1 is identity operator, that is denoted by I. And this is how it is defined, that identity operating on fi should not change that function. It is the same fi. Identity will not change the value of that function. It will give you the same function. Another operator is forward difference operator. So number 2, you write forward difference operator. Forward difference operator. That is denoted by del, not del, but of course that's del operator. How is it defined? It is defined by the forward difference of fi is the same as fi plus 1 minus fi. The next minus the current. That's what it means. So I can also bracket this. That is forward difference. Another operator is the backward difference operator. Backward difference operator, that is denoted by, again, this is del, nabla. It's a Greek symbol, let us nabla. So this is how it is defined, that backward difference of fi is equals to f fi minus fi minus 1. It is the current minus the previous. Another operator, let me bracket this. Another operator is what we call the central difference operator. That is denoted by delta. And it's defined by delta. Let me use another color. We define this as delta of fi is equals to fi plus 1 over 2 minus fi minus 1 over 2. That's how we define the central difference operator. So I'll bracket this. That's number 4. Number 5, we have what is called the shift operator. Denoted by E, and it is defined by E of fi should be able to give us f of I plus 1, f subscript I plus 1. Shift is just when you are at the current, to shift it, you just go one step forward. That is when the power of the shift is one step forward. That's what it means. And lastly, number 6 is what we call the averaging operator. That is denoted by this symbol mu. And this is how it is defined, that mu of fi is equals to 1 over 2, just the average, of fi plus 1 over 2, then plus fi minus 1 over 2. That is called averaging operator. It's just you average those two values. You add them and then you divide by 2. So having defined those finite difference operators, let's now see how to solve questions involving these operators. So for the first question, look at our first question. Let me take you up. Already we have discussed the operators. We have discussed that. Now we are at question 1. Let us solve question 1. Express these operators. Express each of the following differences in terms of the functional values. So they are from part A all the way up to part K. So let's start with part A. Part A is so you write solve the questions, or simply work out the questions. Work out the questions. Number 1, part A. We need the forward difference of F3. Forward difference of F3. Look at the definition of forward difference of Fi. In this case, I is equals to 3. So it will be, remember it is Fi plus 1, so that will be 3 plus 1 minus F3. So this is the same as F4 minus F3. And that's the same as H, the step size. So the other one is part B. In part B, we need the backward difference of F6. So you write backward difference of F6. From the definition, if it is Fi minus 1. So in this case, I is equals to 6. So we'll have F6 minus F of 6 minus 1. And so that will be F6 minus F4. 5. Part C. What do we have in part C is the shift of F4. The shift of F4. Look at how we define the shift operator. Shift of Fi is equals to Fi plus 1. So in this case, I is equals to 4. So that would simply be F of 4 plus 1, which will give us F of F5, I mean. And the other one, part D, the central difference of F5, look at how it is defined. It is F of I plus 1 over 2. So our I is 5. So 5 plus 1 over 2, then minus F of 5 minus 1 over 2, which you can write as F of 5 plus 1 over 2, that is 5.5, which is 5.5 is the same as 11 over 2. 11 over 2, then minus F. Now this will be 4.5, which is 9 over 2. We also have the other part D, part E. We have mu of F5. Just from the definition, it is 1 over 2 of Fi plus 1 over 2. Our I here is 5, then plus 1 over 2 plus F of I minus 1 over 2. Our I is 5. So that's simply equal to 1 over 2 of F of 11 over 2 plus F of 9 over 2. F subscript, those are subscripts, I mean, don't confuse them. And I've told you when we write F subscript I is the same as F of X, I. That's what it means. Now the other one is E squared of Fi. That's part E, part F. We need now, let me use another color, E squared of Fi is the same as the shift of another shift of Fi. So what is the shift of Fi? Work out the innermost bracket. So we'll have shift. Shift of Fi gave us Fi plus 1. Again, when you shift it again, that will give you Fi plus 2. It's just like you are shifting twice. So then this tells us that in general, so take note that in general, when you are shifting k times, the shift, you are shifting it k times, you need to get F of I plus k. That's the general formula when you're dealing with the shift operator. Let us work out the other part. Part G. We now want the forward difference, the second forward difference of Fi. Second forward difference of Fi. It is the same as you split this forward difference of another forward difference of Fi. Look at how we defined this innermost bracket. What was it? So this will be forward difference of, here we got Fi plus 1 minus Fi from our definition of forward difference of Fi. And so this is the same as writing forward difference of Fi plus 1 minus forward difference of Fi. And so you can as well write this as, let's work out the first term. When you are getting forward difference of I plus 1, you take the next minus the current. So the next is I plus 2. The next is Fi plus 2 minus Fi. Then minus forward difference of fi is f of I plus 1 minus, remember this is I plus 1, the next minus current. Then here it is fi. So that if I work it out, let me open the bracket. This is fi plus 2 minus 2 fi plus 1 plus fi. Somebody might be wondering, what are these fi plus 1 and so on? Let me illustrate here. What I did was this one. I picked some consecutive functional values where here we have fi when x is xi. Here we have fi plus 1, x is xi plus 1. This other side we have fi plus 2, no, not plus 2, but minus 1, minus 1. This is xi minus 1. On the left it is fi minus 2, xi minus 2. Now here we have fi plus 2. Here it is x of I plus 2. So when you talk of I plus 1 over 2, is somewhere here, in between. So when you take the forward difference of fi, let's say this, it is the next, which is fi plus 1, minus the current, which is fi. That's what we meant. When you talk of backward difference of fi, it is the current minus the previous, fi minus 1. Averaging, or simply central difference, you need now to consider the midpoints, the value here and the value here. Because here it is fi minus 1 over 2, and here it is fi plus 1 over 2. So we are subtracting this value minus the other value. That will give you the central difference. So I hope that is clear to everyone now. So let's go back. We have found that part H, we need the second backward difference of fi. So now backward difference of fi, that should now be equal to backward of another backward difference of fi. Check how we defined backward of fi, the innermost bracket here. So that will give us backward of fi minus fi minus 1, which you can as well write as backward difference of fi minus backward difference of fi minus 1. And so this should be able to give us, what is the backward difference of fi? That is the same as fi minus fi minus 1. Then I have another minus. What about backward difference of fi minus 1? You can go back to the diagram. Fi minus 1, you want the backward difference. So you are here. When you are at fi minus 1, it is the current, which is fi minus 1 minus the previous, so minus this. So it is fi minus 1 minus fi minus 2. It is current minus previous. Let me comment on this. This is next. It means next minus the current. But this one means the current minus the previous. That's very important. So now we can use that idea to work out this. fi minus 1, that will give us, the current is fi minus 1 minus the previous, which is fi minus 2. And when you open the bracket, you get fi minus 2 fi minus 1 plus fi minus 2. Let's get part. Let's solve the other part, part I. In part I, what do we have? The second central difference of fi. So delta squared of fi, what was it? This is the same as writing delta of another delta of fi. And how did we define central difference of fi? What we have in the bracket, it is the same as fi plus 1 over 2 minus fi minus 1 over 2. That's what we have. And if I open the bracket, we'll have delta operating on fi plus 1 over 2 minus another delta operating on fi minus 1 over 2. Now, work out the first term. That will give us f. Now, where there is I, now replace I by I plus 1 over 2. You see what we have? It will be I plus 1 over 2 plus another 1 over 2 minus f I plus 1 over 2 minus 1 over 2. That's the first term. Then minus the other one is f of I minus 1 over 2. You are adding 1 over 2. The other one need to subtract. I minus 1 over 2, then minus 1 over 2. When you open the bracket, you get, because of course this is the same as f of I plus 1 minus fi, then minus fi minus fi minus 1. And so this is the same as fi plus 1 minus 2fi plus fi minus 1. So that's what we have as the central difference operating on fi twice. But J, we have mu operating on fi twice. This is mu of another mu of fi. So here, check how we define the averaging operator of operating on fi. So this will be the same as mu of f. Remember, there was 1 over 2. fi plus 1 over 2 plus fi minus 1 over 2, and this is divided by 2. It's an average, which is the same as 1 over 2 into, now I take mu inside, so it's mu of fi plus 1 over 2 plus another mu of fi minus 1 over 2. That's what we have. And so this can as well be written as, check our definition of the averaging operator. Let's work out the first term. So this is the same as 1 over 2 in bracket. The first term is this one here. Mu of fi plus 1 over 2 again is 1 over 2 times fi plus 1 over 2 plus another 1 over 2, then plus fi plus 1 over 2 minus 1 over 2. That's average of those two. Then there's this other sign is a plus. Let's work out this other term. This again is 1 over 2 of fi minus 1 over 2 plus 1 over 2, then add to fi minus 1 over 2 minus 1 over 2. So that's what we have here. And now we can be able to simplify. So this will now give us, we can write this equals to 1 over 2 into, of course I can factor out 1 over 2 because I can see there are 2 of them. So that will give us 1 over 4 outside. Inside we have f of I plus 1 plus f of I, that is the first bracket. Then the other one is f of I plus f of I minus 1. And so this should now be able to give us 1 over 4. Here we'll have f of I plus 1 plus 2fi plus f of I minus 1. So that's what we have as the value of mu squared operating on fi. Let's answer part 2, where we need to show, we need to verify those identities. In part A, question 2, part A, we need to show that the shift is equals to I plus, not I plus, it is identity plus the forward difference. So we need to show that shift is equals to identity plus the forward difference. So what is the proof of this part? You know how we defined our forward difference? Yes. Take note that the forward difference of fi is the same as fi plus 1 minus fi. And this you can as well write as the shift operating on fi minus identity operating on fi is the same thing. And you see fi is common, so this is the same as shift minus identity, and that is operating on fi. So if you cancel this and this, that will give you can say therefore, the forward difference is the same as the shift minus identity, or make the shift the subject. So shift is equals to identity plus the forward difference. Let's answer part B. Part B, what do we need to show? That the shift operator is the same as identity operator minus the backward difference operator, and this is raised to -1. So let us prove. Again, we know our definition of the backward difference operator. That should be backward difference. Backward difference of fi, it is fi minus fi minus 1. And so how do you write this? This is the same as the identity operating on fi, because it will not change that value, minus the shift to the power of -1. Remember, in this case now k is -1 operating on fi. I told you e raised to k operating on fi is the same as fi plus k. So in this case our k is -1. And so fi is common, so this is the same as identity minus the shift raised to -1 operating on fi. And so when I cancel this and this one, I'm going to get, you can say therefore, the backward difference is the same as identity minus the shift to the power of -1. So make that shift operator the subject. So you can just say, or the shift to the power of -1 is the same as identity minus the backward difference. So when I raise both sides to -1 or reciprocal on both sides, what do you get? So, or make shift the subject, shift alone is equals to, of course, you take reciprocal on both sides, so identity minus the backward difference, this is raised to -1. The other part is part C. Part C, we can do it here. That is part B. Let's write part C here. In this part, we need to show that the second central difference, or second order central difference is equals to forward difference minus backward difference. So what we do here, of course, you know how we have defined our second order central difference. I don't need to write it again. Look at delta squared operating on Fi, it is this one. And what did we get? Our answer was this. So that's what I'm going to use, because already I've explained how to get to this answer. So let's use it. So that would be Fi plus 1 minus 2Fi plus Fi minus 1. So you can write this, that the proof is that delta squared operating on Fi is the same as Fi plus 1 minus 2Fi, then plus Fi minus 1. That's what we got. And how else can you write this? This is the shift operating on Fi minus 2 times identity operating on Fi plus shift raised to -1 operating on Fi. Or instead of writing that as shift operator, because I want to relate it with the forward and backward, there's no need of writing that in terms of shift operator, but let me write in terms of forward and backward so that we get the relation that we are interested in. So you see, this can as well be written as Fi plus 1 minus Fi of course, let me not put that bracket, then minus another Fi plus Fi minus 1. So when I introduce the bracket, I'm going to have Fi plus 1 minus Fi is a bracket, then minus Fi minus Fi minus 1, another bracket. So what is the first bracket? This is a forward difference of Fi. And the other bracket is backward difference of Fi. So Fi is common, so this can be written as forward minus backward, and this operating on Fi. And so you see now, if I cancel this and this, I now go back to my identity that delta squared is equals to forward difference minus the backward difference. And now lastly, we need to prove part D. The last part is part D, where we have mu times delta. We need to show that mu times delta plus half delta squared. 1/2 delta squared is equals to the forward difference. Let us prove this. You know how we defined the operator mu and the operator delta and the operator, of course, the forward difference operator. Now let's start by writing mu in terms of the shift operator. We said that mu operating on Fi, remember mu is averaging operator, that's the same as 1/2 times Fi plus 1/2 plus Fi minus 1/2. And so in terms of the shift operator, this is the same as writing 1/2 times the shift raised to 1/2 of Fi plus the shift raised to negative 1/2 of Fi, of which this can as well be written as 1/2 times the shift raised to 1/2 plus the shift raised to negative 1/2 operating on Fi, because Fi is common. And you realize that if I cancel this and this one, I am going to get mu is equals to 1/2 times the shift raised to 1/2 plus another shift raised to negative 1/2. Let's also get the relation for delta in terms of the shift operator. So also we know that delta operating on Fi is the same as Fi plus 1/2 minus Fi minus 1/2. So this you can also write in terms of the shift operator. This is how it will be written. So this is equals to the shift raised to 1/2 of Fi minus the shift raised to negative 1/2 of Fi, of which this can as well be written as the shift raised to 1/2 minus shift raised to negative 1/2 operating on Fi. And so if I cancel this and this one, I am going to get, you can say this implies that delta is the same as shift raised to 1/2 minus shift raised to negative 1/2. So now we have those two. Therefore, now let's show that the left-hand side will give us the right-hand side of that equation. So we can start with the left-hand side and show that we are going to land to the right-hand side. In fact, I can write it here. Let me take this to the left. So we can just say that now I want mu times delta plus 1/2 times delta squared, 1/2 delta squared. What is it equal to? Our mu, we have found it to be 1/2. Let me use another color. Our mu is 1/2 times shift raised to 1/2 plus shift raised to negative 1/2. That was mu, this one here, times delta. This was our delta, so we multiply by this. It is shift raised to 1 over 2 minus shift raised to negative 1 over 2. That's negative 1 over 2. Then we need also 1 over 2 plus delta squared. So I can take this here. So you have plus, I said 1 over 2 times delta squared. So delta is shift raised to 1 over 2 minus shift raised to negative 1 over 2. That should be negative 1 over 2. And this should be squared. So remember the binomial expansion. I want us to take note that a plus b squared, a plus b times a minus b is the same as a squared minus b squared. Also, you know that a minus b squared is the same as a squared minus 2ab plus b squared. So we use those binomial expansions to be able to work out this the multiplication in those operators. So here is like a plus b times a minus b. So it is a squared minus b squared. So we'll have 1 over 2 into, let me write that in proper manner. That's 1 over 2. Remember, this is our a. This is our a, and this is our b. Again, this is our a. This is our b. A plus b times a minus b. So we expect a squared, e raised to 1 over 2. When you square it, you get e. A squared minus b squared is e raised to negative 1. Plus another 1 over 2. Now this is again a minus b and you square it. What should it give us? It should give us a squared, which is e, minus 2ab, 2 times e raised to negative 1. 2ab, that's 1 over 2. This is negative 1 over 2, I mean. 2ab, then plus b squared, that is e raised to negative 1. And so this is the same as, I can see 1 over 2 is common, so we have 1 over 2 outside. Inside we have e minus e raised to negative 1. Then I can see plus another e. The question is, what is the value of e raised to 1 over 2 times e raised to negative 1 over 2? When you add the powers, you get e raised to 0, which is an identity. So minus 2 times identity operator, or simply e raised to 0, then plus e raised to negative 1. Collect like terms. That is 1 over 2, 2e. Of course, this and this will cancel. So 2e minus 2 identity. Which is the same as, if you factor out 2, we get e minus identity. E minus identity. But now the question is, what is e minus identity? We got it here. And let me take you back to part A. You see, it is this. E minus identity is equals to the forward difference. So I replace that by the forward difference operator. So instead of that, I'm going to say this is equals to the forward difference operator. So we have shown that the left-hand side will give us the right-hand side. So left-hand side is equals to the right-hand side. So that's how to deal with the finite difference operators. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When you meet next time, we look at more problems involving finite differences. Bye-bye.